Angular momentum is everywhere. It gives us our 24-hour day and our 365-day year. But it doesn't just stop there. Whether it's on this planet or up in the skies, angular momentum is everywhere. Beyond just the 24-hour day and 365-day year, it can affect the sun, it can affect our planet, it can affect exoplanets, it can affect the accretion disks of black holes and neutron stars, and in the grandest of scales, a galaxy. I want to uncover what exactly angular momentum is and how it works. Why don't you join me on this journey? Mathematically, the equation for angular momentum is L equals I times W. We'll come back to L, which is angular momentum, after we talk about what makes it up, I and W. The I refers to the momentum of inertia, which is how much resistance an object holds to its rotational motion. Resistance depends on the amount of mass and how the mass is distributed. If you look around your room, you will find that some objects have less inertia than others. My room, for example, I've got a poster, I've got a camera, I've got a big ball sphere thingamajig. All of these things have different amounts of inertia. They will require different amounts of force to move. That is both because of how much mass they hold, but also because of how they're shaped. W is the angular velocity, the speed and direction at which an object is rotating around its axis, measured in radians per second. Once again, intuitively, the faster an object spins around something, the harder it becomes to stop that object from spinning, telling us that angular velocity contributes to resistance. I'm no pro at Blender, but I tried creating an example of resistance using speed. Here's what I have. There are two balls in this simulation. The one on the left is the faster one of the two, so in other words, the one on the right is the slower one. The point of this simulation is to show how speed contributes to resistance. When I play this video, you'll find that the one on the left is harder to stop than the one on the right. If we come back to L, angular momentum, we see that it is a product of I, which is resistance dependent on the mass and its distribution, and W, which is speed and direction that also creates this resistance. We can intuitively understand that angular momentum represents the intensity at which an object spins. Now we must talk about the conservation of angular momentum, which greatly applies to many worldly objects. The principle goes as follows. If there is no outside force on your system, angular momentum will stay the same regardless of changes within the system. Here's the really cool part. Assuming there are no external forces, if we increase one of the variables, we will see the other variable decrease to keep angular momentum the same. For a planet, in this case our Mother Earth, which we all know very well, if we increase W, the angular velocity, we see our planet become smaller, and therefore the size or moment of inertia, I, decreases. If we increase I, the moment of inertia, we see angular velocity decrease, and therefore the object spins slower. It's so cool to imagine that if our Earth became smaller, we would see our days pass by much faster. Angular momentum can be seen on any body orbiting in the axis of rotation, which means every one of our planets, the sun, neutron stars, solar systems, galaxies, and many other objects. But it's not just all the way out there, it's also here. If you have something spinning, you are looking at angular momentum, and I think that's really cool. If you want to learn more about science related stuff, subscribe and like. I think you're gonna like this channel. Peace out.